All right, so yesterday we started our unit on fractions and looking at how fractions are related to each other, looking at patterns in fractions, how we can model fractions. Today we're going to start looking at fractions in the context of real life. How do we use fractions every day? So let's start talking about that. How do we use fractions in everyday life? Charles?
Like if you're on the, if you're like racing on the track, you could put a timer and see how much time you ran, and it would probably be, if you wanted to run 1.5, that would be one track that you would run, so you could use that as a fraction.
So you're talking about the distance that you're running around the track, so we use it for distance measurements. What's another way that we use fractions in real life? Brody?
Like if you cut up a pizza, you can figure out how many slices you slice up to the pizza, because you have 8 or 10 people and you need to have the same pieces.
Okay, so we divide a pizza into pieces for the people that we're serving. Angelica?
Like if you want to buy a car or something and parents split the money with you, you got to know how much money you are going to pay and parents will pay or something.
Okay, so if you're looking at, you're each paying a fraction of the car, so when we're paying for objects. Any other ideas, Kaylin?
Cooking.
Cooking. I use fractions every single day when I cook recipes for my family for supper. So I have to use half of a cup of milk or a quarter cup of sugar, and we're using all kinds of fractions definitely in cooking every single day. Anytime you're looking at a part of a whole. Or we also learned that it could also be part of a what?
Set.
Part of a set. So any of those things would be real reasons that we would use fractions. Today we're going to look at word problems that include fractions so that we can see real life situations that we use fractions. Our focus for today is we're looking at what strategies can you use to determine if fractions are equivalent. We looked a little bit yesterday at models and how we could use models to determine equivalent fractions. Today we're going to take that and add to it when we look at other strategies that we can use besides the models when we're using mathematics and mathematical thinking to help us determine if fractions are equivalent. So let's start off with making sense of our problem. On Monday, Coach Owens ran part of a mile. On Wednesday, she ran part of a mile. On Friday, she ran part of a mile. Does that sound like Coach Owens?
Yeah.
Yes, she likes to run. On which days did Coach run the same amount? So what is this problem about? Kyron?
How many miles you ran?
Okay, are we wanting to know the total number of miles she ran? Okay, so it has to do with miles, but what is it specifically asking us about miles? So which days, Monday, Wednesday, or Friday, did she have the same amount that she ran? What information is going to be important to us for solving this problem? Angelica?
How many miles she ran each day?
How many miles she ran each day, or what fraction of a mile, since we're learning about fractions, she ran each day. We're going to need to know that information to determine what's the same. All right, so let's see how you apply your strategies from yesterday. I'll give you the numbers. On Monday, Coach Owens ran 2/3 of a mile. On Wednesday, she ran 4/5 of a mile. On Friday, she ran 4/6 of a mile. On which days did Coach run the same amount? All right, solve. could you demonstrate that and prove that with a model? How can you prove it with a model? Okay, does your model prove your equation? As you finish, you know I'm going to challenge you to say, how can you prove it with a model? Let's share our thinking with one another. Please, could you come up and share with us? All right, so turn to talk. Remember to use your discussion starters, either sharing the strategy you use, and if you're not sure how to find the answer, explain your thinking so far. All right, share. Strategies that you've come up with now that you've had an opportunity to share and clarify your thinking. Stella, could you come and share your strategy?
This side I put 2/3, 4/5, and 4/6, and then I colored in all the boxes and see which one lined up. And then what I did was then I put 2/3 and 4/6. And how I tricked it was 2 times 2 is 4 and 3 times 2 is 6.
All right, so let me just go over it. So Stella basically lined up the portions. Now, why was it important that all of her fraction bars in this square are the same size? Angelica? remember I told you that when we're comparing fractional parts, we have to start with the same whole. I can't compare the size of the pieces of pizza if I'm comparing a small pizza to a large pizza, because the holes are not the same. So Stella used a really great strategy in lining up her models here by creating one large square, or actually rectangle, and then cutting it into the 3 pieces so that she knew each of those pieces started out as the same size hole. Then, trying to get her pieces as even as possible, she was able to determine 2/3 and 4/6 in the model were equivalent. I love how Stella checked herself mathematically. That she knew that if she was doing twice as many pieces in the numerator, then she also had to do twice as many pieces in the denominator for it to be equivalent. Nice strategy. Rosa, could you come and share the model and strategy that you use? All right, so explain your thinking.
What I did is I did 2 times 4, which is 4. Wait, 2 times 2, which is 4. Then I multiplied 3 by 2, and multiplied 6, which is equal. And then I did the circles. I did a circle and then divided it into 3, and I put 2 parts of it, and then I did a circle and then divided it by 6. And I put it 4.
So you did the opposite thinking from Stella. You started with solving it mathematically, doubling the parts in the numerator and the denominator, and then proved it by putting your model to see did that prove that your statement was correct. Nicely done. Lamarte, could you come up and share the models that you drew? Lamarte took the challenge and drew multiple models to demonstrate his thinking.
First, I knew it was 2/3 and 4/6 because I times 2 and 2 times 2 is 4 and 2 times 2 is 6, but I wanted to check myself. So I did the number line model, and then the circle model, and then the fraction model. And they were all equal.
Okay. So I like that you tried the number line model that we just started talking about this week. What did you do first when you were creating this? How did you determine that 2/3 was equal to 4/6 using this model?
I drew 2 lines, and then for the 2/3, I drew 2 lines, and I found the 2/3 and broke it down, and then I added more lines in between the 2 lines, and I got 6, and then I found 6/4.
Okay, so Lamarte's saying that what he did there is he started out dividing it into thirds, and he put this was his 2/3 mark, and we know that it's the space between. And remember, on a number line, we do want to put our range, so it would also be good to have your 0 and 1 just to show you're talking about part of a whole and where you're placing it. And then he knew that 6 was 2 times as many pieces, so he cut each piece in half again and determined 1, 2, 3, 4, 6 is what would go there, so that he could use the number line to also prove that 2/3 is equal to 1/6. Thank you, Lamarte, for sharing your strategies. So if we determine that 2/3 is equal to 4/6, then ultimately what was the answer to the problem? On which days did Coach run an equivalent amount? Kaylee?
Monday and Friday.
Yes, it was Monday and Friday. So here's just to demonstrate one other way that you could have done it, and some of you already captured this thinking in your strategies. Coach Owens ran the same amount on Monday and Friday because 2/3 is equivalent to 4/6. Some of you did use this model as well. That was the one I taught yesterday, where you can start out with your original fraction of 2/3. And we know that 6 is 2 times as many parts, so we're going to cut each part in half, and then count, and we have 4/6. And then some of you are using what you've seen on iReady, in the lessons, which is multiplying the fraction by a fraction that's equal to 1, so it has to have the same numerator, same denominator, to get an equivalent fraction. Let's see if we can make some connections to what we're doing. First of all, I'd like you to talk to your partner. What strategies can we use if we need to determine if fractions are equivalent? Name off as many as you can think of to your partner to give us some extra tools in our toolbox for the problems we're going to solve today. Alrighty, turn and talk. Alright, who would like to share what your partner said would be a good strategy for determining if fractions are equivalent? Alex. Okay, so he likes where you place the models on top of each other and line them up with that same hole so that you can see from your visual model. Okay, what's another strategy that a partner shared? Haley?
My partner said that he can use like a fraction bar to mixing up the equivalent.
Okay, so another visual model with the fraction bar, which we said is easier for a fourth grader to draw often than the circle model and actually divide it evenly, so that's another great strategy.
I taught my child that you gotta underline and turn 2, turn 2, and the other line and circle.
Alright, so Dawei, you like the number line, and you like being able to multiply it by a fraction that's equal to 1, like 2 over 2. Alright, Brody, what did your partner share?
She said that her teacher taught her a butterfly method. Like first, you line up the numbers, then you circle the numbers that are across from each other and multiply them together. And if they're not equal, if they're equal, you have a circle in the middle and you put the equal sign.
Okay, the butterfly method is a method often used by teachers to check. However, I caution you that the butterfly method does not demonstrate understanding. So when I'm looking at your models today, the butterfly method is not a model. It is a strategy for checking your answer, but it doesn't really visually show why the numbers are equivalent or not equivalent. So be cautious when you're using what we sometimes call the tricks of math, that those tricks can help you check your work. And that's often why they're invented, is a way of checking. But I wouldn't rely on them to demonstrate understanding of equivalent fractions. I would rely more on using your visual models or your multiplication methods to demonstrate that you understand why the fractions are equivalent. What I have found over the years is that students that use the butterfly method usually cannot explain to me why it works. They just have learned the trick, but they don't know why the fractions are equivalent, how many more parts does one have than the other, those things that we've really wanted to focus on in class. So be cautious. I'm not saying it is a bad strategy. I'm saying it would be a better strategy for checking yourself after you initially use one of the other strategies we've learned in class to show your understanding. Second question. When you multiply any number by 1, the product is equivalent to the other factor. For example, 6 times 1 equals 6. 32 times 1 equals 32. 100 times 1 equals 100. So anytime you multiply by 1, you end up with the same number you started with. That is equivalent. It's the same amount as what you started with before you multiplied. Why does multiplying the fraction below by 2/2, create an equivalent fraction. We'll have you first turn and talk. So turn to your partner. Why do you think this works when you multiply by 2/2?
I think that works because and
Alright, stop. Who would like to share out your ideas on why this method or strategy works in creating equivalent fractions? What are your thoughts, Kaylee?
I thought that the time 2 times 2 equals 4, so they put the 4 on the top, and then they did 2 times 2 equals 6, so they put the 6 on the bottom.
Okay, and it is a true equation. I agree with you there, that if you do these steps, you're going to end up with this. My question though is why? Why can you do this math and know that the fraction is going to be equivalent without even needing to draw a model, that you know this is going to work every time? Stella, what do you think?
Because it can only be times, and 2 times 2 is 4, and 3 times 2 is 6, and both times 2.
Well, what if I did this? Do I know that 8/12 is an equivalent fraction to 2/3 from this equation? Angelica?
The reason the fractions that work is because you're doubling it, and when you're doubling it, you're getting another fraction because you're just adding it together. So if you want to get like another equivalent fraction for it, you just double it by even.
All right, well, what about this? Is 2/3 equivalent to 6/9? If you need to, prove it. Prove it on your board. Is 2/3 equivalent to 6/9? Does that equation work? Show me a model. Prove it. James, kind of demonstrate how how you proved whether or not that equation is correct. Explain your thinking.
Put the box into thirds, and then I shade in the two, like in the fraction, 2/3, and then I drew two more lines to represent the three we were multiplying by, and then I looked at the shading, and then I counted, and I got 6, and then I counted each box, and I got 9. So 2/3 is equivalent to 6/9.
Okay, so thumbs up if you agree with James that your model proved that this statement is true. All right? Why? I'm not doubling it. Thank you, James. I'm not doubling here. I'm not doubling here. But yet this still works if I use mathematically the same numerator and denominator when I multiply. It still works. Why? Angelica.
The reason that it can work is because as long as you can multiply it by that number and get the same number, it's like an equivalent. It's equivalent back, so it's going to be right. As long as you can do just about as long as it's the same, just about anything. As long as it's the same number and it's in the same number.
What do you mean the same number? What has to be the same?
Product.
Well, I don't have the same product here. My product is changing each time. Who'd like to add to what Angelica is sharing, maybe to clarify? Maya?
It's equivalent because 2 times 3 is 6, and 3 times 2 is 9.
Okay, and I agree, it is equivalent. I'm just trying to figure out why. There has to be a mathematical reason why this works. Rosa?
I think as long as you have the same numerator and denominator whenever you multiply, it's like gonna get you an equivalent fraction.
I want to ask you something. If I were taking those numbers, what whole number are these both equal to? Brady?
One whole.
One whole.
Because
If we multiply any number by 1, do we have an equivalent amount?
yes, ma'am, because 4 divided by 4 is 1, and 3 divided by 3 is 1.
Okay. So when I multiply by a fraction that has the same numerator and denominator, I'm basically multiplying by 1, which we know mathematically, any number you multiply by 1, you end up with an equivalent or the same amount as what you started with. Now here the number changes. When we multiply 6 times 1, we get 6, because we're dealing with whole numbers. And here the number is changing, the numbers in the fraction, the numerator and denominator, but the amount is not changing. Just like we can say 6 is equal to 6, I can feel confident knowing that 2/3 is equal to 6/9, because when I multiplied by 3/3, I was basically multiplying by 1, because 3/3 is equivalent. The only difference is I'm cutting more parts. I'm tripling the parts. I'm quadrupling the parts. I'm multiplying and cutting it into more parts, but I'm not changing the amount of the whole that is being focused on. All right, today you're going to apply the mathematical thinking we just talked about, as well as what we learned about with our partners about modeling yesterday, in some partner work. So I'm going to give each partner group a problem to solve. You're going to create a visual model to demonstrate your thinking, write an equation that supports your model, and that equation needs to demonstrate what fraction equivalent to 1 are you using in solving the problem. You'll have to write the final answer, and then I want an explanation. I've been having you explain orally how you solve. Today I want you to explain in writing, like we do on our mini posters. How did you solve the problem? And then, of course, as always, check your work afterwards. Partners check each other. Is it accurate? Is it neatly written? What else will I be looking for posters that will be worthy of the hallway? What does a poster need to be? What are some things that will make a poster worthy of putting it in the hallway? Neat. What else? Abigail? Okay, so you may want to add some color. And you know we have our color pencils and where our markers are.
Make sure you put your name on it.
Definitely has to have the names of who's working. Chris?
Halloween stuff.
Extra math thinking. So I'm going to definitely be looking for, did you show me more than one model? Does your math thinking support your model or vice versa? Does your math model support your math thinking? So definitely that extra, going the extra mile with your math is important. Stella?
Organized.
Organized. You may want to solve it on your whiteboard first. Angelica?
Correct. Correct.
Accurate. You know, I don't put anything out in the hallway that isn't the correct answer. Maya? Say that one more time. Yeah, definitely need model or models. You can use more than one. That check your work. All right, so you've established what the expectations are if you want a poster that goes in the hallway. When you finish this and it is checked, and I'll be circulating while you're doing that, then your independent work is in the yellow folder, and you can come up and get your independent work and do that, and it's generating equivalent fractions. So you work as a partner group. You're going to work with your shoulder partner today.